Okay, hi everyone. So like I just said, my name is Rioko. And today I'm just going to share with you a little flavor of some of the work I've been up to so far. So I'm going to be discussing the heterogeneity in the Triassic Sherwood Sandstone reservoir, specifically in the Larne Basin within Northern Ireland. Okay, so the Sherwood Sandstone Group as an important resource in Britain and Ireland. So here we have a location map showing the present-day sedimentary basins containing the Triassic Sherwood Sandstone Group. So the outlines, if I get my pen. So yeah, the outlines in yellow are showing the extents of the Sherwood Sandstone, and then the highlighted yellow sections are showing the outcrops. Now, why is the Triassic important? So historically, it's been used for hydrocarbon exploration in the past. So from the prior research and studies, we know that this reservoir contains good porosity and permeability. Now, I'll touch on the definitions of these in a short while, but just for now, those are two crucial factors that we need to be looking at when we're thinking or considering any sort of injection or abstraction into the subsurface. Now, the Sherwood Sandstone is being utilised or investigated for geostorage applications. So as highlighted with the coloured dots, the blue ones are showing proposed carbon capture storage sites, and the orange ones are showing proposed or ongoing geothermal sites. So I've kind of expressed that this is an important resource. We know that it's good for porosity and permeability, and it's now being used for different geostorage applications. So why do we even need to look at it further? And the reason we do need to look at that is because quantifying heterogeneity is really complex. One of the best ways I sort of try and think about it is if you kind of like imagine a plain cake, like a Victoria sponge, that would be classed as like homogeneous. So the variations in rock properties aren't going to be that great in that. If you compare it to like one of those marble cakes where you put some chocolate and done loads of swirls into it, that's going to cause variations within that cake. And similarly in rocks, we see those variations within the rock properties. And that's the thing that's really hard to constrain. And that's what we're trying to look at here when we talk about heterogeneity. So the Triassic succession can be classed into three subdivisions. So we've got the Sherwood Sandstone Group in mainly the lower Triassic, going up into the middle. And then this is overlain by the Mersey Mudstone Group. And then we've got the Penarth Group at the top. We also have the Haggerston unconformity, which is represented by this like squiggly line. So why are there different formations within the Sherwood Sandstone deposit? And one of these reasons is the depositional environment. So here we've got different color codes. So mainly if you look at the Sherwood Sandstone, it's like this pale yellow color, which indicates fluvial sandstones. And when we use the word fluvial, we are talking about river deposits. We also have this sort of highlighter yellow identifying the Aeolian sandstones. And these are associated with wind deposits. So we see some of those deposits in the East Irish Sea Basin, Central Irish Sea Basin, the Kish Bank, and also the Cheshire over here. So this is one of the reasons we sort of separate and like subdivide the Sherwood Sandstone because of the different deposition environments, which in turn can change the grain size and the sorting. So let's just look at how all these deposits got here. You know, how are they all this Sherwood Sandstone but have different formation names? Well, this can be related back to the paleogeography. So way back when, 250 million years ago, we lay a lot closer to the equator in the supercontinent Pangaea. So in this tiny red thing here is island of Britain. And we're quite inland, so the green mass is land, and then the like brownish stuff is mountains. So it's quite restricted from any sort of marine influence. So it was a pretty dry climate. So at the time of deposition, when at the end of the Permo-Triassic, we were like lying in this sort of region, and then due to tectonic activity, different provenance sources, which is basically where the sediments come from, that began to diversify these basins. And on the right here, we have the present day map, but I've just drawn on some arrows showing the main drainage basin systems. So one of the main ones that was feeding the Triassic basins within the UK was the Ballynesis River system, which is this huge 400-kilometer drainage system which carried river deposits, so the proximal sort of coarser grains at the beginning, and then as you move away from the source, getting towards the distal part, more finer grained. So Northern Ireland here, the provenance hasn't really been studied, and there has been some research by Franklin who suggested that the sediments here have been sourced from at least 2 drainage basins, one coming from the north and one coming from the south. So the provenance controls the sediment deposits in different basins, and this can help cause heterogeneity. Okay, so the heterogeneity is the variations within the rock properties. And when I refer to porosity, I'm talking about the amount of open space within a rock. So if you imagine like a sponge in the bathroom or whatever, those sort of holes, those are the voids that can sort of hold the water. And you want more porosity, that's a good thing. So here we sort of quantified it as poor porosity being less than 8% and good porosity being greater than 20%. But this is kind of give or take. And then we have the permeability. So how easy is it for these fluids to actually move between the spaces of a rock? So how easy is it to sort of extract or move fluid through? So the bigger the holes, the more likely the fluid will be able to pass through easier. So here on the left, we have a generalized schematic. It's not exclusive to Northern Ireland, but it nicely summarizes the different parameters that can cause heterogeneity. So as we've already mentioned, we've spoken about the depositional heterogeneity, how river versus wind deposits can deposit different sediments. We then have the silicified zone here, which is basically when the rock has been cemented, specifically by quartz cement here. So this really, really reduces the permeability of a rock. And here, sort of what I was mentioning before about that sort of marbled cake look, we've got this Sherwood Sandstone Group here with a schematic showing the different layers of mud that can go through, and that can cause baffles to flow. Interestingly, for Northern Ireland, they have been affected by these igneous dikes and sills. So in the Paleogene volcanism, these have intruded into the Sherwood Sandstone, and obviously that's going to block the porosity and the permeability. Another thing to explore is the diagenesis. So diagenesis is how the rock changes as a result of pressure and heat. So, 250 million years ago when the Triassic was deposited till now, the formation has probably experienced, pressure, temperature, and all of that stuff has caused changes to the rock, and that can therefore cause heterogeneity. So just to sort of summarize in, word form, the differences between the depositional and diagenetic controls. So with the diagenesis, when you're adding heat and pressure, thermal exposure to a rock, it can cause the dissolution of minerals and new ones to grow. And due to the climate, the provenance, grain size, all those things can also affect the heterogeneity through depositional environments. Okay, so let's have a little look at the projects going on in Northern Ireland. So this map here is showing the top to the Sherwood Sandstone, like the maximum temperature at the top interval. So this like corally red is highlighting the hottest temperature seen in this side of Northern Ireland. So that's about temperatures up to 100 degrees, which lies about here on this geothermal resource classification. And that's absolutely ideal. In Northwest Europe, at the minute, the biggest issue and the biggest problem we're facing is decarbonizing heat. So, we want to be utilizing the Sherwood Sandstone if we can to help sort of decarbonize the heat and help meet our climate goals of 2030, 2050, and so forth. So a couple of projects that have been going on throughout Northern Ireland. So Queen's University Belfast have employed 2 closed-loop systems in the Riddell Hall and their Maclay Library. They also have open-loop systems in the Lyric Theatre and also the School of Biological Sciences. Coca-Cola have actually been utilising the Sherwood Sandstone for groundwater. So they've been utilising that water to help the production of Coca-Cola. And most recently, the Geoenergy Northern Ireland project has been looking in two demonstrator projects specifically for geothermal in the Stormont estate and in the Greenmount campus. So before we move on, I just kind of want to just bring attention to this graph just to sort of show that, you know, the need for heterogeneity sort of studies and looking into the porosity and permeability changes. Because if we look at this section here, which is showing the porosity in the Loughnane Basin, we can see that if we look at the average porosity of all the well data from these basins, we can see that the highest recorded porosity is in the same basin where the lower porosity was recorded. So just because we're in the basin that has the highest porosity doesn't mean that's going to be the same, you know, throughout the entirety of the deposit of the reservoir. And same with the permeability. In the Larne Basin, in Millidarcies, the permeability reached the highest of 167. But then it was recorded down at 6 millidarcies also. So this is just one thing to consider in terms of, you know, why heterogeneity is really important to study. Okay, so hopefully I've set the scene enough there. So now we're going to jump into, well, back into the main project aims and what I've been looking at here. So in the middle, we have the main question. So trying to understand the vertical reservoir heterogeneity in the Southern Larne Basin. And then around here, we've just got some critical questions that we want to answer to sort of answer that main question. So if we work clockwise, we start here, you know, what changes in porosity and permeability are we seeing that exist as we go deeper in the column? What is the main cause? What is the main control causing these heterogeneity that we're seeing in this basin? And, you know, the heterogeneity that we're seeing, is it exclusive to the Southern Larne Basin, or is this a laterally extensive issue? Is it happening in the basins west to where we're looking? And here, when we're discussing, is it a part of the Omskurt formation and is the Hagas and unconformity present? We're trying to understand if we can sort of correlate and understand how the Larne Basin fits into that stratigraphic column that we just looked at. And finally, we've got, you know, looking at the implications for geothermal energy. So what has this data told us about future geothermal applications within the Larne Basin? So around the edge here, I've just put like the main things that we've been doing to sort of answer this question. So obviously data collection, looking at wireline logs, understanding the depositional environment, getting into the field, looking at the outcrops, looking at thin section, grain size, core logging, and specifically the lithophagy scheme. And just to sort of enhance this point, because we're going to be looking at this a bit more in the PowerPoint, but when I'm talking about lithophagies, I'm talking about how we can sort of break up the Sherwood Sandstone into mini sort of repeating sections that we see throughout the formation. Okay, so let's look at where I'm collecting my data from to sort of establish an answer to the questions that we just spoke about. So to begin, I'm looking at, or I have looked, should I say, at the Kilroot borehole, which is highlighted by this purple dot. And the reason we began with this one is because the Kilroot borehole is the only borehole to core the entirety of the lower Triassic. So it's got a full suite of the Sherwood Sandstone Group. And obviously when I'm trying to understand, you know, the heterogeneity, how things have changed, break it up into some sort of lithophagy classification, it's one of the best place or the best place to start. We then incorporated some outcrops just to sort of understand and get a better idea of the heterogeneity in the area. So we've chosen these based on just exposure and proximity to the starting location. And then to sort of answer that question, we just discussed about, you know, is this an exclusive problem to the Southern Larne Basin, or is this the heterogeneity we're seeing, you know, regional? Is it lateral extensive? So to answer that, we sort of brought in Woodburn Forest, which is nearby, and also Annockmore borehole too. Okay, so how does the Triassic reservoir quality change across Northern Ireland? So this might look a bit scary, but we'll work through it together. So if we start with Kilroot, and we start with this first track here, this is GR, so that's the gamma ray. So in short terms, the gamma ray sort of picks up the radioactive elements within the formation, and the higher the number, the more sort of mud rich that formation is. So the more peaks it has towards the right, the higher mud content, as opposed to if it's closer to the left, that's more of a clean sandstone. The fascies, I'm going to pause for a minute because we'll come back to that in a second. But here, this grey track here is the friability. So when we're talking about friability, this is basically residual sand. So you know when you go to a beach and you can literally just pick up sand in your hand and just play with it, that is residual sand, and that's really friable. So we can see here that the friability is laying in this uppermost section. And then here we've got the permeability. So highest permeability to the right and then lowest permeability to the bottom. We don't have density log for Kilroot. It wasn't due to drilling issues. So what we can do is look at a nearby well, which does have density data. And what we can use the density data for is to sort of interpret porosity. So what we've done here is highlighted the sections where porosity is greater than 16%. And we can see here that at Woodburn Forest, which is very close to Kilroot, only 4 kilometers away, as we go down with depth, the porosity is reducing. We're seeing less of that shaded blue. Same over here in Annockmore, way over here. We're seeing as we go down with depth, we're decreasing the porosity. And in terms of permeability in Kilroot, we can see from our data here that it's decreasing with depth. We can also see just from looking at this, if we carry this across, if we just look at the trends, we can see that this deposit, the upper Sherwood Sandstone, is thinning towards the west. So that tells us a little bit about the tectonostratigraphic evolution of the area. And just to give the thermal gradient, in Kilroot, it's about 21.3 degrees. Okay, so time to look at some rocks. I'm sure you're all very excited. So now I'm going to break down my fascie scheme. So when I was going through Kilroot, I looked at the core and I broke it up into mini fascies based off their grain size, structures that I was seeing, and sort of tried to understand the different causes of each sort of lithofascies and the environment. So first up, we have the clean cross-stratified sandstones. So these are fine to medium grained with rare intervals of mudstone beds. So we've classed it as less than 10%. So here you can see what I was trying to just explain about the friability. So I hope you can see clearly, you know, this is very residual sand. You can literally pick up with your fingers and it will dust away, as opposed to being in more of a consolidated state in the core. And this really nicely shows the high angle crossbeds that are associated with this clean cross-stratified sandstone fascies. Here we have similarly clean cross-stratified sandstone, but the difference between these is the angle of the crossbeds. So in this section, we had lower angled crossbeds, and that tells us that the environment is slightly different. So here we had a high energy fluvial channel environment, but here we're having a lower energy environment. And then we also have the thinly bedded ripple laminated sandstones, which are very fine to fine grained, and also have a low percentage of mud clasts, but they have higher intervals of ripple laminations, as nicely seen in outcrop here. And all of these are related to river deposits, so all fluvial environments. Now, here we have the heterogeneity sandstone. So this is basically, I guess, a good example of that marbled cake that we were talking about before. So here we had the sandstones is the main composition, so it's about 70%, but up to 30% of that is mudstone interbed. So there's mudstones integrated, as we can see here, that's been mushed together in deformation, and there's also drapes of mud in the top here, and they went up to 2 centimeters. On the flip of that, we have the heterogenetic siltstone, so where it's mainly siltstone up to 70%, but there's also 30% sand. So here you can see a sand-filled mud crack. So this is an example of how it's, you know, mainly mud, but there is that sort of sandstone that needs to be captured and identified. And then we have the pebbly granular sandstone. So this, as you can see again, we've got huge soft sediment deformation up here in terms of like the elongated mud class being squished. You can also see the different variations in mud class sizes. So there's quite small ones here. These are really angled at the bottom compared to these like large sort of squeezed and stretched out ones at the top. So this is really going to impede on the permeability. And all of these deposits are also associated with fluvial environments. So again, river deposits. Then we have the mudstones. So these are the sections which, primarily, just mud. And yeah, so these are a lot more laminated clay stones, and these are associated with floodplains. So still river deposits, but they're more like the banks where there's not a lot of energy and it gives that time to the muds to sort of settle. Now we're going to move on to an example of aeolian deposits. So as I mentioned before, the aeolian is the wind deposits, and we didn't see any of those in the Kilroot borehole, but we saw some at Outcrop. So this is at Scrabo Quarry, and here we saw evidence of wind-blown aeolian dune forms. So if you imagine this little hump is a dune form, this is kind of the sediment being cascaded over the top and like falling over the side of the dune. And then we also saw evidence of damp interdune bed forms. So sometimes like between the dunes, there can be a bit of like mixing of, like the damp environments. And that can be seen here with the ripples you can see just above the pen. Okay, so before I sort of go on, how have I sort of determined what facies is kind of good, variable, and poorer in terms of porosity and permeability? Obviously, we don't have porosity data here, but what I have done is I've inferred porosity from proxies. So the sizes of the grain is one proxy that we can use to sort of understand the porosity and the grain size as well. We then also chose the cross-bedded sedimentary structures. So these are more associated with the river channels. And so if there was crossbedders there, I associated that with, being, the facies that we want, and it is going to have a good porosity and permeability. I also incorporated the permeability data that we had. And also we tried to make sure that the ones which were deemed as good were the ones with low intervals of mudstones and ripple laminations and clasts. So this just kind of shows the permeability readings for each of the classifications. So the ones that are deemed as good, deemed as variable, obviously because they're variable, one of them's higher than the good and one of them's lower, but that's, variability. And then we have the low ones here, poorer ones, so I say. I've grayed out pebbly granular sandstone because this data is quite anomalous. We got one of the highest readings of a permeability out of all of our samples in a facies which isn't commonly deemed as to have good porosity and permeability. But so that's kind of been popped now. But this is the way we sort of graded it all. Okay, so now I'm going to show you a bit more of like a zoomed in sort of capture of Kilroot borehole. So I went there and I logged the very upper section of Kilroot. So we started at 250 and went down to 295. This whole section in the middle is just the key. And then this is just showing you where we are on the map again. So if we look at the logs here, I've color-coded the facies in terms of what we just discussed. So based off those parameters, I've color-coded it, the traffic light system. So green, good, red, poorer, yellow, variable. So we can see here that predominantly there's sections of good facies, or the facies which are associated with good porosity and permeability. This orange section here is the friability, so that sort of residual sand we was talking about. And you can see that it's very, very common in this upper section, quite exclusive to the green facies. So we can assume potentially that, that's a sign of like improving the porosity and the permeability. The cements are highlighted by these like patched sections, and the cemented sections are quite low in this. And there's not a huge amount or a huge abundance of cemented sections here. And now let's compare that to the lower. So we can see here that straight away, it's looking a bit more heterolithic. There's more sort of intervals of like this mixture between mud and sandstone compared to the upper section. Also, just to bring to your attention, the cement. So before it was more sporadic and not even that much. In these sections, we can see that the entirety of the core was cemented. This is mainly calcite cement. So when I poured the well, not poured, I did drown it, but just with the little plops of HCl, it was fizzing. So it's a sign that this is a calcite cement. However, there is still a good proportion of the facies associated with good permeability and porosities. And here they took an RCal, so it's just a routine core analysis, and like a core plug, and we have some data for that. So they got 19.2% porosity, which is great, and 74.2 millidarcies, and that was in the good facies section. So take a message from those two comparisons. In the upper Sherwood sandstone, we have more coarser grained facies with a high proportion of the high sandstone to shale, and there was a lot more friability. In this section, in the bottom section, we have no section of friable parts at all. And what I just want to bring us to now is a couple thin section samples, all from that one sort of facies, which I have deemed, good porosity, good permeability will be good for, this research. So I have a couple slides showing the same facies, but we'll kind of see, the heterogeneity that can be there. So this is at 259.5. So yeah, it's this one here. And so we have a lot of, well, not loads, but, quite a bit of blue here. And that is showing the void. So where how porous it is. So there's quite a bit of blue here. And you can see here the cement that we was talking about. So this cement sort of comes in behind the grains, and it's kind of like a glue. It's basically cementing it together. And it's hardening the rock. And it's removing all of the porosity and potential permeability. So this is one of the sections. Now we're going to go slightly down in the core. And even though we're in the exact same facies, you can see here that the grain size is a little smaller. There's still quite a lot of blue, so quite a lot of porosity. In this section, we don't really see too much cement. There's like a little clast up here. And we also see these dissolved pores in this section. So we think that there was a grain here, and over time, due to temperature or fluid interaction, something's been dissolved here because it's too much of a big space for it to just be there and not be compacted down. In the same facies again, we've got this interstitial detrital clay. So, even though we said it's rare, it's still less than 10%. So there are sections where the mud sort of blocks that blue porosity and really hinders the amount in this section. And again, same facies, but this is now from like very, very bottom of the core at 720. Oh, here we are. And yeah, so there is still porosity, but the grains are a lot closer together. There's not a lot of space between them. And yeah, we also have these muscovite grains, which is not great for the permeability because that really can block the pores and stuff. And then finally here we have an example of one of the variable facies. So this is one which is mainly siltstone, but with some sand. So you can see that, compared to the others, there's a lot less blue here. It's just this teeny bit here and these clear sort of lines of, the mud coming in. So this just sort of shows, even in one facies, there is still so much variability at the micro scale. Cool. Okay, so now we're gonna park the route for now, and I'll show you some of the outcrops. So here is Scrubber Quarry, and this nicely shows the Paleogene sills. So you remember I mentioned at the beginning that in Northern Ireland they was affected by the Paleogene volcanism. So these are igneous sills which have intruded the rocks and it's really nicely shown here. So, oh, okay. So I took myself down to the quarry. So say you stood here, that photo I showed you is like here, but way, way higher in the sky. And yeah, I took 2 logs. So I did one at this face and one at a face, which is like a 15-minute walk away. And here we recorded evidence of the dune facies, the interdune facies, and we also saw some sections which were related to a fluvial facies. So here where we had, the rip-up clasts, and in this section where we had some pebbles and some mortar escapes. But this is a mixture of the fluvial and aeolian deposits. Okay. Then we went to Strangford Lock. So if you look at the map, Kilroot is here, Scrabo is here, and we've just come down to the blue dot here. So thanks to Alistair for this lovely drone picture. So we actually logged this section of the outcrop. So this is all the Sherwood Sandstone Group. So went out down there and logged the section we could see. So here we have, we went from 0 to 98.5. And here we can see, there's quite a lot of the cross-stratified sandstone, but a lot lower angle. So this is like the low angle crossbeds with a couple mud clasts. It's predominantly the green facies, so the one which we're assuming based off the sedimentary structures, the grain size is good, and a few sections where it's got the more muddy sections. And then finally, we have Sea Park. So here we have a lovely example of how, we've got the crossbeds going down here, and then it's being cut over by these planar laminations. And here, in comparison to Strangford Lock, we do have some sections where we've got the more high angle crossbeds, but it's still predominantly the lower angle crossbeds facies. So, takeaway point from these points, or these slides, should I say? The fluvial channel facies, so the ones which are associated with river deposits, are dominant in Kilroot, Sea Park, and Strangford Lock, whilst Scrabo has a mixture of both. It has the aeolian and the fluvial deposits too. So what trends are we seeing here? So sort of following that traffic light system and looking at the 3 outcrops that we've discussed, as well as Kilroot, what are we seeing? Well, straight away, of course, we can see that in Scrabo, we didn't associate any of the facies we saw there with the poorer facies. Compared to all the other ones, the lower Kilroot sees, quite a bit of the poorer facies in there. But overall, they have all the places that we've seen in the outcrop and the core do have a high proportion of, this good facies. So mainly, a high section of sandstone as opposed to the shales. And one thing, that we should sort of consider and we're looking into is at Scrabo here, yes, we've got really good facies, all associated with good porosity and permeability. But here, this outcrop, that's where the igneous intrusions are. So in thin sections, would it still be the same? Or would we be seeing things that, would have caused, reductions in the porosity and permeability? We also need to further this and do some correlations. So Scrabo is like up on a hill, it's like 80 meters elevation or so, compared to Strangford Lock. So once we do our correlation, we might be thinking, okay, well, was the aeolian sediments ever here and then it's been eroded away? We don't know. But just looking at what we have now, we can see that overall, the research so far, is suggesting that the depositional setting, so the different, the fluvial and the aeolian, that sort of drives the facies development and the grain size, and our dominant primary controls on heterogeneity. Okay, so if we was just to look at the gamma ray and the permeability and the friability, we might think, okay, well, the permeability is reducing with depth. looking at the spikes, we're seeing more, more spikes commonly towards the bottom, and then it's getting less and less as we go up. And the friability is all within this upper section. So surely if we're following our traffic light scheme, we might be thinking, okay, well, down here it's going to be the poorer, and as we move up, it's going to get more green. And I kind of already showed you the answers, but as we know, that's not necessarily the case. So yes, in the bottom section, in the very lower part of the Sherwood Sandstone group, I've just broken it up here into A, B, C, and D, just for little markers. But you can see that as we're moving up, there's not like a direct trend. It's not like, oh, well, it's, all green in the top and only reds at the bottom. Even though that the upper section does have a high proportion overall of sandstone to shale, it's not to say that it doesn't have any sort of varying or poorer facies. So what is this telling us? So we've got the permeabilities again, and just to compare the lower to the upper, I've just broken up these numbers so it's a bit more easier to see. But what this slide is telling us is that even though facies does play an important role, there's something else that's controlling the porosity and permeability. What is it? Don't worry, that was a rhetorical question. But one other thing that we're going to look at now is grain size. So now let's see what the grain size does and if it plays a role. Okay, so this is showing, so what I did was I measured the grain size in each thin section, or these thin sections, should I say. And what we can see is that as we go down kill route, we see that grain size is decreasing with depth. And that sort of correlates to the data that we're sort of seeing with the gamma ray. So as we're getting further down, we're seeing an increase in the muds, and muds are commonly lower grain size as opposed to sandstones. So what could be causing this trend that we're seeing? So perhaps, sort of integrating again what we was discussing before about deposition environment. Maybe, at near the bottom where we're kind of coming out from the Permian into the Triassic, we were at the end of maybe a distal supply. And then over time, as these sort of influx of two provenance sources come in, we're seeing an increased sediment source, and the grain size is therefore picking up at the top. Another takeaway point. So even though the facies plays an important role in grain size, there still must be other controls. What are they? And this is something that, I'm now investigating and trying to look at. Okay, so to sort of summarize all the stuff that we've spoken about, here I have a schematic model sort of illustrating the early to middle late Triassic deposition environments across UK and Ireland. So this isn't exclusive to Northern Ireland, but yeah, just what we think could have happened. So the lower diagram here, or the lower block diagram, should I say, is showing the terminal river systems. So it's splaying into a downstream sort of player lake here. And as we move up into the upper block diagram, we're showing more of this, dry land braided river system. We've got some evidence of aeolian, so aeolian dune fields and some sand sheets. But, it's not as if it was, wet here and then completely dry here. What's been happening is that there's been some sort of cyclic events. So, alternative wet to dry systems. And then as we go up, it's generally becoming more arid, as seen with the aeolian deposits. Okay, so let's conclude with the main outcomes from this section of research. So predominantly, fluvial channel facies host properties of better reservoir qualities. So that's when we're looking at the cross-bedded sandstones with the low intervals of mud. The facies most heterogeneous are the intervals of the varying grain size, higher shale proportion, and this is showing that the grain size is really key when it comes to reservoir quality and heterogeneity. So, those sections that I showed you with the photos, so the sand and mud are like properly deformed into each other. Those are the sections which are obviously going to be a lot more heterogeneous than the cross-bedded clean sandstones that we saw also. In the Kilroot borehole, the porosity, permeability, and grain size increase with depth, and the good porosity is seen to correlate in samples with the mud content. And, you know, in the final slides we discussed, the facies does play an important role, but there must be other controls. So we're looking into petrography now, looking more into the thin section samples, and we're sort of coming up with ideas or reasons as to what's sort of controlling this. And as we move from the lower Triassic sediments to the upper, we're noticing depositionally that it's transitioning from a prograding river to sort of more of an increase in frequency into more of in a more drier climate. So what's next? So as I just briefly mentioned in the previous slide, we're now going to be looking at characterization of reservoir quality and the diagenesis. So now we're going to be looking a lot more into the thin sections and the petrology, and trying to understand the diagenetic controls on reservoir quality and understand the evolution of the sandstone. So how much is being compacted, how much cementation's occurred, how much the minerals have dissolved, or how many minerals have grown. And then we'll also be doing an impact, burial history. So this is when we sort of see how the reservoir and the basin has interacted with the thermal exposure, burial, pressure, effective stress, and sort of understand the history of the basin from a burial and temperature aspect. So yeah, thank you. Those are the references throughout if anybody wants them. And yeah, thank you a lot for listening.